we continue now, resume our day, start our day with, again, Dimitri Bilic talking about energy minimization problems.
Yeah, thank you very much. Thanks for making it in this rain. Okay, so I'm going to continue talking about some energy minimization problems. I will briefly review some of the things that we talked about yesterday. And I'll start with some very famous energy minimization problems in which, I'll start with discrete energy. These are problems which are famous, but there are more questions than answers in those problems. So probably the most famous one of these problems is the so-called Thomson problem. So basically what it asks is if you have n electrons on the sphere and you want to find the equilibrium positions of those electrons, what will it be? Right? So, and by equilibrium position, I mean just the interaction under the Coulomb potential, okay, and that would give you precisely this interaction here. So this is a discrete energy in the sense that we defined last time. Here the kernel is discrete, so we do not have the diagonal terms, of course. Okay, this problem has its own Wikipedia page, okay, so which tells you probably it's pretty famous. It was posed by Thomson. Okay, all right, now we know that it was based on an incorrect model of an atom, but okay, who cares, right? And also it's also it's interesting by itself, and it has interpretation. If you have electron particles in a charged sphere, they would be on the boundary, and then yeah, it's a question that makes a lot of sense. And actually, it's a question that if you were to ask a similar question in one dimension, there would be no doubt as what the answer is, right? And in one dimension, you have equally spaced points, and usually it's not even super hard. In many situations, not super hard to prove that equally spaced points give you the minimizer. As soon as you go one dimension up, you go to S2. You already don't have good candidates for most values of n. You don't know. If I tell you put 100 points on the sphere, it's not clear what the best configuration should be. And the answers to this problem are known only in really a handful of cases, so 6 to be precise. Okay, and in most of these cases, the minimizers are what you expect them to be. Okay. The only case that among these ones that is a little bit more delicate, well, not a little bit, it's actually significantly more delicate, so the case of 5 points. Even with this very low number, this is actually a pretty recent result of Schwartz, and it's a computer-assisted proof. It's heavily computational. And it's for 5 points, it happens to be the bipyramid. Okay, so you put 3 points on the equator and 2 poles. Okay. You can also notice, for example, that the cube is not there. The 8 points, you don't have 8 points, that's not solved. And the cube will not be a minimizer, that's not. Actually, computationally, you can go to the Wikipedia page. There are lots of computational candidates for minimizers, but almost, well, nothing else is proved. So these are the only things that are known. Okay, there are other closely related and similar energies. So in particular, when you can consider other values of S, okay, in other dimensions also, not just on S2. In particular, well, when S is D minus 1, that's so-called the Newtonian or Coulomb case. There are other interesting things. For example, when S is 0, the proper replacement for this is the logarithmic energy. You replace the kernel by the logarithmic kernel, so that's also a very interesting problem. There has been a lot of work on it recently. Yeah, again, the answers are known in the same cases. One thing that you do, so if you increase the values of n, you don't really know what would happen to the minimizers. One thing that you do know is that as n goes to infinity, minimizers will be uniformly distributed, and that's actually pretty easy from our discussion from yesterday, because you can check that these kernels are strictly positive definite. Okay. And okay, we just talked about continuous kernels, and these are singular, but most of the theory actually goes through, and they are conditionally positive definite. So if you look at measures at energy integrals, then the uniform measure minimizes this. And then general theory tells you that as n goes to infinity, especially since the uniform measure is the only minimizer, well, any minimizer for large n has to be, has to be uniformly distributed. Another thing that makes all of these problems so hard is, there are, unlike the frame energy, which we discussed yesterday, here there are lots of local minima which are not global minima. So even computationally, it makes things very, very challenging. It's not easy to search for minimizers, okay? And even harder to prove things. Okay, then there is an interesting case if S goes to infinity. So when S goes to infinity, well, LP norms become the L infinity norm, right? When you take P to infinity, it becomes the maximum. So here, this becomes the best packing problem. So you want to maximize the minimal distance between points. Okay, so and this has a name. It's known as Thames problem. Thames was a botanist studying pollen on grains. And here, for the best packing problem, if you're on S2, answers are known for a few more values of n, so it's a little bit more, but still not a lot. Okay. All right. All right. You can also consider negative values of S, that is positive powers, and actually tomorrow this will be a big part of tomorrow's lecture. Of course, in this case you maximize instead of minimizing, otherwise you just put everything into one point. Okay, so this is sometimes referred to as the Fayet-Stott problem, finding points that maximize the sum of distances. And even not in the sphere in general, this is a pretty common object in discrete geometry, in metric geometry, finding points that maximize the sum of distances. It tells you something about the structure of the metric space. Okay, so, right, so again, the answers are known in a handful of cases. The exact same cases. So again, 5 is again a computer-assisted proof. But the other cases, actually, it's not a coincidence that you know the answers in the same cases, because there is a certain effect called universal optimality, and I will mention it a little bit more at the end of the lecture today. So this was done. This goes back to Kohn and Kumar, that certain configurations, certain really nice configurations become universally optimal, meaning they minimize energy for really large classes of functions simultaneously. Okay, and that's exactly what happens. And those configurations that you get for 2, 3, 4, 6, and 12 are exactly, they are universally optimal. So you can guess, well, I said it's natural candidates, but I think everybody knows what those get, right? For 12, it's the icosahedron, right? For 6, it's going to be the octahedron, right? Or the cross polytope. Okay. All right. Yeah, and this when S actually equals 1, so you just have the sum of distances. It's closely related to the to another interesting object in discrete geometry and approximation, the so-called spherical cap discrepancy. There is an identity which we will see tomorrow that relates the two quantities directly. All right. And so, okay, I will go through the next few slides really quickly. This is just a brief review of what we did today. So now from discrete energies, let's turn to energy integrals. Okay, so right, we want to minimize over, probability measures. Again, technically this kernel could be singular. Okay, but as I said, most of the theory goes through. We figured out yesterday that positive definiteness is a property that plays a very important role. So let me very quickly remind you about positive definiteness. This is the definition. These were our first examples, right? So you started with the just the inner product in a N is positive definite, then powers, then positive linear combinations of powers. So those were positive definite. And we figured out that on the sphere, if you want it to be positive definite in all dimensions, those are the only examples. Well, what if the dimension is fixed? We'll answer that in a moment. Okay. Yeah, and we have this formulation, which I will mostly use formulations in terms of measures. Okay, so you can just pass from the discrete formulation to the continuous formulation. Right. stop me if there are any questions. Yeah.
So can you go to the previous slide?
Sure.
So your question is which measure which measure minimizes the integral
Oh.
with this kernel, right?
Yeah, so if you're given a kernel, the question is which measure minimizes the integral. And we gave some answer, at least in the case of the sphere, when the kernel is rotational invariant, we figured out that positive definiteness is the property that makes sense. That gives you the uniform measure in a minimizer. But now I want to look at this again, and also I want to understand how can we say what happens when other measures are minimizers? What happens if you don't have positive definiteness? Okay. All right. Okay, so we'll also, yeah, so conditional positive definiteness means that this holds for mean zero measures. Yeah, strict positive definiteness, strict conditional positive definiteness means that it holds for mean zero measures, and it's zero only if nu is zero. So, all right. So let me actually mention a few facts that are related to the facts that I mentioned yesterday, but they will come up later in the talk. So this comes from basic calculus of variations potential theory. So if you have a minimizer, you can check that K has to be conditionally positive definite on the support of the minimizer. You actually don't have any information, because it's really one of the ways to prove it is by considering the Hilbert-Schmidt operator with this kernel and this measure, and then it doesn't really tell you anything about what happens off of the support. Right? So, but it will be conditionally positive definite on the support, and that's why in the theorem that I mentioned yesterday, we actually needed full support for some implications. Okay, also it's standard potential theory. This was discussed yesterday. If you compute the potential, if you integrate once, and if you get a constant on the whole domain, then this measure mu has to be a minimizer. This is provided that the kernel K is conditionally positive definite. Okay. Okay. Well, also if you have conditional strict positive definiteness, so strictness essentially leads to uniqueness of minimizers. Okay, so I'll come back to that, but now let's go to the sphere, okay, and let's go to the sphere of fixed dimension, and unlike yesterday's lecture, here D will stand for the dimension of the sphere, okay, so yeah, the frame theory people, they always use, of course, D for the ambient dimension, so here I will be working mostly in the sphere, so D is the dimension of the sphere. Okay, so I may be using not the most conventional notation, but the important object here will be the Gegenbauer polynomials. So they are polynomials that are orthogonal with respect to this weight. Okay, this weight arises very naturally when you integrate in cylindrical coordinates on the sphere, integrate rotational invariant functions. I will actually, in a moment, I'll get back to it, and I will tell you how to, in mnemonic, to memorize this specific power. It's actually, yeah, and so they're closely related to spherical harmonics, in particular through the addition formula. If you take spherical harmonics of fixed degree, you have this formula here. So if you take any basis of you have this sort of tensor product structure. Okay. And this tensor product structure will give us positive definiteness, but let me actually first tell you about the mnemonic. Let's look at this power that you get here. Oops, sorry. Yeah, so the power is d minus 2 over 2. Right? That power disappears if d is 2. Well, that factor disappears in d is 2, so that factor is just a constant. That's the Jacobian, when you integrate in cylindrical coordinates over the sphere, the Jacobian disappears. You might remember it from calculus. And actually, this is known for more than 2,000 years. This is a famous theorem of Archimedes, sometimes referred to as the head box theorem. It tells you that if you take a ball and a cylinder of the same radius, so ball inscribed into a cylinder, and you cut it horizontally, the areas of the strips will be the same. Okay. So legend has it that Archimedes really liked this result and that he had it engraved on his tombstone. his tombstone did not survive to our days, but there is a legend that Cicerone found his that tombstone, that he recognized that tombstone by that drawing of the cylinder and the ball and the sphere. Okay. This also is known as the Lambert cylindrical equal area projection used in cartography. So it's a projection. So that's exactly, you project, you wrap things around the ball and project, right? And the interesting thing about it, it preserves areas. It really distorts some of the linear dimensions, but it preserves areas. Okay. Okay. So anyway, so the way to remember that power is that d minus 2 over 2, it disappears when d is 2. Okay. And this is exactly Archimedes' theorem. Sorry, just a little historical detour. Okay. So the addition formula tells you that Gegenbauer polynomials are going to be positive definite. Whenever you get this tensor product structure, you get positive definiteness almost for free. Well, let's check that. Let's compute the energy with an arbitrary signed measure here. Okay. Well, you write this to put the integrals inside, and now this integral just splits into a product of two identical integrals, and so that's non-negative. Right? So that's it. That's the whole proof. So now you know that Gegenbauer polynomials are positive definite. You also know that this means that any positive combination of Gegenbauer polynomials is positive definite, right? And turns out that these are the only ones. So that's also a theorem of Schoenberg. I mentioned this last time, so this is a very old result, very classical from 1941. I mentioned the second part last time, we discussed it. So if you want to be positive definite in all dimensions simultaneously, it's only analytic functions with positive Taylor coefficients. If you want to be positive definite on a sphere of a given dimension, the Gegenbauer coefficients have to be non-negative. All Gegenbauer coefficients are non-negative. You can actually even say more, interestingly. So if you have a continuous function so that all the Gegenbauer coefficients are non-negative, there is a very interesting self-improving property. In this case, the series automatically converges uniformly and absolutely. Okay. So this could be proved in different ways. You can prove it using properties of Gegenbauer polynomials, using certain things about pointwise behavior, the fact that they're maximal at 1, actually. But you can also view it as a general fact, a consequence of a theorem from spectral theory, a very standard theorem, Mercer's theorem in particular, that says that, well, if you have a kernel of a positive Hilbert-Schmidt operator, then the expansion converges absolutely. Let me actually state this really briefly, because we might return to it. So I was told the chalk and the board are very nice. So basically, if you consider this operator, let's just do things on the sphere. Well, if we did this on an arbitrary domain, okay, you would be able to say that if this kernel is positive definite, then this would be a positive operator. So this is a Hilbert-Schmidt operator. It's a positive operator, so you have positive eigenvalues, and you can write the kernel. Okay. And again, I'm doing it in the sphere, but I should really be doing it in general. You could write it in this way. Okay, where these guys are non-negative. Okay. And Mercer's theorem says that in this case, this expansion converges uniformly and absolutely. Okay. And again, technically, this is for an arbitrary domain. But on the sphere, we actually, so these are eigenvalues, these are eigenfunctions. On the sphere, we know immediately what the eigenfunctions are, and the eigenfunctions are exactly spherical harmonics. Okay. And these things, if you group according to the degree of the spherical harmonics, you get exactly the addition formula. You would get the the Gegenbauer polynomials back. So it follows from this fact. It's actually quite interesting that normally the spherical harmonics are introduced as eigenfunctions of the Laplace-Beltrami on the sphere, but they're also eigenfunctions of Hilbert-Schmidt operator on the sphere with any rotational kernel. So in this rotational invariant. So in a sense, well, so this fact is known as the Funk-Hecke formula. The fact that these are spherical harmonics. All right. So you have this nice self-improving property, which makes it really easy to work with such kernels. All right. So then let me summarize a few things. Now, actually, everything but part 3 we already discussed last time. Okay. That's on the sphere. Minimization by the uniform measure is equivalent to conditional positive definiteness, right? But now we also know conditional positive definiteness is actually equivalent to the fact that all Gegenbauer coefficients are non-negative, maybe except the zero order one, the constant term. Of course, if you change the constant term, if you make it go up and down, it's the same thing. The minimizers are not affected. Okay, so you have this equivalence. So now that this gives you a way to directly find for various kernels whether or not the uniform measure minimizes the energy, you can compute it's Norton normal basis. You can compute the coefficients. In some cases, you can do it directly using the Rodriguez formula or some other consideration. In some cases, you cannot compute, but you can prove positivity. In some cases, that at least allows you to check things numerically. But now let's say we completely understand the case of the uniform measure minimizing energies. Let's see what happens if it doesn't. So say you don't have positive definiteness. So let me remind you 2 facts from some of the previous slides today. Okay, so if you have any minimizer of the energy, then the kernel has to be conditionally positive definite on the support of the minimizer. Okay? And also we just discussed that the uniform measure minimizes if and only if the kernel is conditionally positive definite on the whole sphere. Right? Okay, so now what does that mean? Assume the uniform measure is not a minimizer. So the kernel is not positive definite on the whole sphere, right? That means that there has to be a minimizer. That means that if you take any minimizer, it has to have strictly smaller support. It cannot be supported on the whole sphere, right? Because if it were, by fact 1, K would be positive definite on the whole sphere, and then you'll get sigma as a minimizer. So either energy minimization leads to uniform distribution on the sphere, or if not, you have strictly smaller support. It gets concentrated somewhere. So this is the first instance of this thing where you have minimizers that live on smaller sets that get somehow localized or maybe even discretized. Okay. Let's look at some examples of where that happens. So here is this is a pretty standard, pretty classical theorem of Bjork. Actually, it's a very nice paper from 1950s, but it does a lot about energy, about Riesz energy with positive powers and arbitrary compact subsets of Rn. Okay, and what Bjork proves is that up to a certain point, if alpha goes up to 2, well, this also extends to negative values of alpha, but let's for now just talk about positive. So here you want to maximize because it's positive powers. So up to the power 2, you have a unique maximizer. The domain is arbitrary, so you don't really know what it is, but it is unique. And actually, that's one way to show it is strict positive definiteness. Bjork does it differently, but you can do it from strict positive definiteness. And then, oops, sorry, I keep pressing the wrong button. We'll get to that slide in just a second. And then something happens as you pass this critical value 2, and you can prove that minimizers beyond 2 are discrete. So these are discrete measures. So it's at most d+1 points on the support. So, if you specialize to rotationally invariant kernels on the sphere, you can take this even further. Okay, you can say even more. you can say that, okay, you have the same breaking point, same phase transition at alpha equal to 2, independently of the dimension once again. But for alpha greater than 2, you just get mass concentrated at two opposite poles, 1/2 and 1/2. Okay, and when alpha is equal to 2 at the phase transition, you can easily characterize the maximizers as just all measures with center of mass at 0. Okay. Basically, also it tells that at alpha is equal to 2, you have maximizers of very different structures. It could be the uniform measure, it could be two poles, it could be something else, it could be, it could have any dimension that you want between 0 and d. So on. And this is a typical situation where you have some phase transition like that. Usually at the phase transition, you have this huge family of very different maximizer, and it feels like the energy as the parameters change and it hits the phase transition, and then it's decided, okay, here I have lots of options, where do I go next? So it feels like it's doing something like this. Right, so here is a picture which slightly similar. For a equal to 2, this identity is how you prove that you get barycentric measures. So the integral just splits into a product, and you get x d mu of x. Okay. So we had this alpha equal to 2 phase transition in Bjork's result. There is a similar result from just a few years ago, so 2017 by Carilla, Figali, and Patacchini, where apparently they were not aware of Bjork's result because they don't cite it, but this phase transition that they encounter here is exactly the same. The setup is slightly different, but philosophically it's more or less the same, because they work on Rn, but the kernels are attractive repulsive, and they go to infinity. So the kernel looks like this. It starts at 0, it decreases for a while, then increases, and it becomes positive. Okay. So it's here you have repulsion, and here you have attraction, and that attraction does not allow the minimizers, the guarantees that minimizers exist, does not allow particles to fly off all the way to infinity. And what they prove is that if your kernel behaves as negative r to the alpha at the origin, and alpha is greater than 2, and this is the same value 2, actually, then minimizers, global minimizers have to be discrete. With finitely many points on the support. I don't want to do the proof now, but if anybody is interested, I can explain the idea of the proof after the lectures in just a few lines, actually. And it has to do with positive definiteness. Basically, you try to show that, you try to, if the minimizer is not discrete, you try to show that on this sequence, that if you have a condensation point on the sequence that converges to a condensation point, you can violate positive definiteness. Right, so basically we see from two different points of view that this weak repulsion leads to existence of discrete minimizers. So when alpha is greater than 2, that means that this here is super flat near 0, so the repulsion near 0 is super weak, right? And it makes sense. If the repulsion is weak, then particles might glue together, and you would have discreteness. Right? However, it turns out that this is not the only reason that leads to discrete minimizers, that leads to discretization. In particular, so there is an interesting example. Let's still be on the sphere, and let's switch the metric from Euclidean to the geodesic. Okay? And if you look at what happens here, the situation is very similar. But the break is happening at alpha equal to 1 and not alpha equal to 2. Okay. There is the particular reason that will become a little bit clearer tomorrow, but it has to do with the global structure. It actually has to do with the fact that up to constant, the geodesic distance, it's an odd function, essentially. Okay. So d of xy plus d of x minus y equals pi, right? So it's additive. So and it has to do with that fact, and that global, for alpha equal to 1, that leads to existence of many other optimizers. In particular here, at the phase transition, also the structure of optimizer is a little bit stricter. So here it has to be symmetric measures and not just barycentric. But otherwise, the situation is very much the same. Okay, so here is the picture. Okay, so you have symmetric at this phase transition, and you have the same things below and above the phase transition. Okay, and just as a reminder, we had something very similar for the Euclidean, okay, where you had the phase transition at alpha equal to 2, but otherwise it was really the same type of behavior. So for a while, it led me to believe that maybe this is the same in all reasonable metric spaces, maybe with sufficiently many symmetries and so on. Turns out that it's not true in the counterexample, where we don't understand everything completely yet, but it's but we already know that it's getting really complicated and weird. The counterexample is the geodesic distance in the projective space, on the real projective space. So if you do the chordal distance on the real projective space, then the situation is exactly the same as the Euclidean in the sphere. Okay? But if you do the geodesic distance in the projective space, and it's actually related to some conjecture, so it was not just a whim that we started looking at it, then you don't have just one phase transition. It seems that you have some continuous cascade of phase transitions and things, and you don't get the uniform measure until sometime much later, and in higher dimensions you only get the uniform measure in the negative range of exponents and not positive. So for some reason, which I do not completely understand yet, the projective space with the geodesic distance becomes super complicated. Unlike all of these examples, in particular the geodesic distance on the sphere, which seems that you would think that it would behave similarly. Okay. Right. But back to these examples, the main takeaway is that it's not just about the repulsion. It's not about only about the local behavior of the kernel, because if you look at the geodesic distance and the Euclidean distance, they locally behave the same, right? Okay. All right. So here we saw quite a few examples already where you get discrete minimizers. I want to talk about some others. Well, in particular, let me mention, I alluded to this a few times yesterday, let me mention spherical designs. So this is a very, very famous object. So spherical designs are essentially sets of points on the sphere which integrate polynomials exactly up to a certain degree. The question of their existence, it was known for a while that they exist for n large enough, okay? But it was proved actually just, oh wow, this was 12 years ago already, okay. So this was proved by Bondarenko, Radchenko, and Vyazovska, so that's actually the first annals paper of Marina Vyazovska and Danila Radchenko. They proved that there exist spherical designs of optimal order. So this is essentially the order of the dimension of the space of polynomials on the sphere of degree up to m. Okay, so this is basically how many equations do you need to solve to find those points. Okay, so and at least asymptotically, there exists spherical designs of that order. So that's a very nice paper. Actually, in one of the summer schools, I just took one lecture. It's an annals paper that you can teach in one lecture. Well, modular some preliminaries. It's super nice. Yeah. It's I think Danila was still an undergrad when they proved this. Yeah. One thing I want to mention here is that spherical designs can also be characterized in terms of energy minimization. In particular, well, if you take any Gegenbauer polynomial for a given degree, then this sum has to be 0 if this is spherical design, if and only if this sum is 0 for all n, for all degrees up to m. And so this is energy minimization in the following sense. This sum, we just figured out that those polynomials are positive definite, right? So this sum for an arbitrary set of points, this sum is non-negative, okay? So this, and so it's only going to be 0 if you get a spherical design. By the way, one thing that I just recalled and I want to mention it is, we'll give an alternative proof of one of the things we talked about today. If you compute the second Gegenbauer polynomial in any dimension, it's actually going to be, well, depending on which normalization you use, it's going to be a multiple of t squared minus 1 over d. Okay. And now if we use it in this, well, we know that for an arbitrary set of points, this is greater than or equal to 0. Right? If we use that, we will actually get that. So if we plug in this polynomial into the inequality and then just put d on the other side, we have n squared terms, and you'll get n squared 1 over d. We get the frame energy inequality from the fact that this is the second Gegenbauer polynomial. This is an alternative proof of the same fact. So it sort of ties everything together. Okay. All right. So now we know that so spherical designs can be characterized in terms of energy this way. Let's see what we can say about the integral energy. By the way, I have a question. Until what time do I have? Because it's until the hour, right? Until 10. Perfect. Yeah, thank you. Yeah. So if the kernel of the energy is a positive definite polynomial, so it's a polynomial whose Gegenbauer coefficients are non-negative. Since it's positive definite, we know the uniform measure minimizes the energy. But also, since it's a polynomial, we know that if we take any spherical design, that will give you the same thing as the uniform measure, right? The discrete sum is equal to the integral. Okay. So that tells us since this is the minimum, this is also the minimum. Okay. So in this case, you know that if you have a polynomial, a positive definite polynomial, you necessarily have there exist discrete minimizers. Okay. So we were with actually, almost all the work that I will talk about from now on is together with Alexei Glazyrin, Ryan Matsky, Josiah Park, and Alex Vlasuk. Yeah, so we were able to extend this statement to say the following. If you have any kernel where the number of positive coefficients is finite, okay, in particular, well, polynomials work, of course, so this extends polynomials. But here you can have infinitely many negative coefficients also. Then there exist discrete minimizers, and the support of the minimizers contains exactly the number of points corresponding to the dimension of the spherical harmonics where you have positive coefficients. Okay. So, So basically, this tells it for any polynomial there are discrete. There exist discrete minimizers because for any polynomials you have just finitely many positive coefficients. And also it tells you that well, you can also prove that if you have a polynomial that's not conditionally positive definite, you can show that the support of the minimizers will have empty interior. So if the polynomial is not positive definite, that there exist discrete minimizers because they exist for every polynomial, but then all minimizers have to be small in some sense. Right? This is probably not sharp. We can probably say even more. We can probably say that the codimension has to be at least 1, but I'm not 100% sure about that. But this is proved. Okay. All right. And now I want to recall. So this is something we proved. Okay, any questions, by the way? Yeah, sorry, I know I'm moving fast, but I want to get to the one important slide. Here? Yes. Yeah, so if you have an energy with a polynomial kernel, so there are two things. So you know that for any polynomial kernel, there always exist discrete minimizers. There might not be unique. There might be other minimizers. Like here, sigma could also be a minimizer if it's positive definite. But if it's not positive definite, so sigma is not a minimizer, we know already that support has to be strictly smaller, but moreover, in this case, if it's a polynomial, we know that the support has empty interior, so it's really small. And I suspect that you should be able to say something about the dimension of the support, but I'm not yet 100% sure.
So it's maybe like not discrete, but it's still.
Right, but it's still small, right? So there might be minimizers which are not discrete. There might be like one-dimensional minimizers, for example, but they must have small support, right? Okay. Yeah, so these are the inequalities that we discussed yesterday, discussed quite at length, right? And basically well, here we're taking the inner product and raising it to some power. And basically the question is, what happens if you raise it to different powers? Okay, what happens if you, well, even like take power 3, for example. What would happen? What would happen with the minimizers? We know that in this case, when it's an even power, absolute values don't matter. So these are actually polynomials. These are positive definite polynomials. So everything that we know applies. So there are lots of different minimizers. In particular, sigma is a uniform measure is a minimizer, but you have others. You have, say, tight frames. By the way, tight frames are essentially two designs. If you take a tight frame, which is also barycentric, that's a 2 design. That's exactly equivalent to being 2 design. Yeah, but what happens if you put other powers? Then this kernel becomes non-smooth, which is a little bit of a problem. And well, there has been some work. So this was initially I learned about the problem in the paper of Martin Ehler and Kazuo Kujo from 2012. So we know what happens when P is 2. You have a bunch of different minimizers. So they showed, and this is actually a very simple argument. You just compare P less than 2 and P equal to 2. They show that if you go below 2, the only minimizers are discrete, and they're the vertices of an orthonormal basis. Okay. Up to symmetries, of course. Again, this is a problem. You can choose, you can switch x and minus x. So instead of the orthonormal basis, you can also take the cross polytope. So you can redistribute the mass between the point and its opposite. Right, but up to those symmetries, it's just the orthonormal basis. And basically, the idea is that the orthonormal basis is the only tight frame for which, where the inner products only take the values 0 plus minus 1, okay, or 0 and 1. Okay. Okay. But then, well, what happens if you go above 2? Okay, as we discussed, if you're in the even integer, you're again in this situation where you have spherical designs, you have the uniform measure, so you have lots of different minimizers. What happens in between? Okay, we already knew from a result of Ehler and Kujo that here you only get discrete minimizers, only the orthonormal basis. So we started doing some experiments at first. So luckily I had Sasha Vlasuk on the team. He's very good with computations. So this was at the ISORM program a few years ago. And I remember I asked him, could you check what happens, say, for P equal to 3 on S2? And then next morning he comes with the plot, and he says, look, I threw like 1,000 points on the sphere, and the gradient descent, look, it's an icosahedron. So they collapsed into vertices of an icosahedron when you minimize this energy with P equal to 3. And then there were lots of other numerical experiments, and they figured out that it seems that no matter what you do, minimizers, when you're strictly between even integers, minimizers are going to be discrete. So again, this interesting effect comes into play, even though technically the local repulsion here stays the same, right, in terms of the local repulsion, in terms of the distance. Okay, so what in the last 6 minutes, okay, I'm going to mention the theorem that we were able to prove. So we still have a conjecture that it happens for all those intervals between even integers. We cannot yet prove the conjecture. We can prove some partial results. So we have, in particular, this result, which says that if you have a tight design, so the definition is here, and it's actually not even the original definition, but it's the definition that works for us. It's equivalent to the original definition. Basically, tight designs are designs of the smallest possible cardinality. Okay. they need to have, turns out they need to have a lot of good structural properties, and one of those structural properties, which I state as a definition here, is that I don't expect you to memorize the numbers, but basically the philosophy that you should understand here is that you have a design of sufficiently high order, but at the same time it has few different distances. Okay. So that's what will play a role. Okay, and if you have that, then on the corresponding interval between even integers, those discrete structures minimize the p-frame energy. Okay. And also you have some sort of universality here, universal optimality. They minimize it simultaneously on the whole interval, so for all of the functions in this interval. Okay, so this is the list of known tight designs of odd order to which the theorem applies. So the 600 cell here, that's it's not a tight design, but it just misses being a tight design by a little bit. There is one power that it misses, and then it's good again. So it's really weird, which means that sometimes you can adapt the methods and still make proofs go through. So 600 cell is also included in the theorem, actually, but requires a separate proof. And the last thing that I want to do in the last 4 minutes, that should be enough, I want to explain the method. So this is a very, very popular method that comes up in many problems in discrete geometry, best packing, spherical designs. It seems that it has never been used for integral energies before this work, but I think it's for integral energies. It seems that it works in even cleaner ways. So I will explain the method. I will do just a specific case where on S2 p is equal to 3, we have the icosahedron, so that's the case with which the whole work started somehow. And I will show how you prove that the icosahedron minimizes the energy. Okay. So a couple things that we need to know about the icosahedron. The icosahedron is a 5 design. And if you take the set of all the inner products of points in the vertices of the icosahedron, it's plus or minus 1 or plus or minus 1 over square root of 5. So you have few different distances. Okay. All right, so here's what we're going to do. And as I mentioned before, the correct way to do it would be on the projective space, and then you would have to use Jacobi polynomials. Let's not worry about that. Let's do it on the sphere, but with even polynomials. Okay. So I'm taking my kernel. So the red is the kernel f, absolute value of t cubed. Okay. And now I'm going to do Hermite interpolation. Okay, so I'm going to interpolate it by even polynomials at the points that come from the icosahedron. Okay. So this method, unfortunately, only works perfectly when you have a candidate. Okay, so I interpolate it here, and here interpolate both the value and the derivative. Okay, so these 2 data points. Okay, and because the derivative matches, that's guarantees, it's not immediate, but it's very simple. It guarantees that the interpolant doesn't cross, that it stays below. Okay. And I interpolate here also, but here I only interpolate once. I don't care if it crosses, that's fine. So I use 3 data points, and since it's even polynomials, I get a polynomial of degree 4, right? Constant term square in degree 4, which is cool because this is a 5 design. So that's nice. Okay, so I have these properties. I get a polynomial of degree 4. It lies below f. It matches f at those points that are important. The important part is this. It's positive definite. Okay. When you're doing it with just one function, you can just check it by hand. Okay. Just expand it into Gegenbauers and you'll see it. When you're doing it for a class of functions, that requires proof, and that's actually the hardest part of the whole thing. Okay. Proving that what you get is positive definite. Okay, but then once you have it, I have 40 seconds, and I think that's enough. Okay, so let's start with this energy. Okay, so first of all, well, h is smaller, so I can bound it from below by the energy with h. Okay, well, h is positive definite, so I can bound it below by the energy of the uniform measure. Okay, icosahedron is a 5 design, and this is a degree 4 polynomial, so things work. So this is equal, right? And now f and h, they match precisely at the values that are important here. So you get this. Okay, well, that's the proof. Sorry, 4 seconds late. Okay. All right, I'll stop here.
Thanks a lot.